I'm Bruce Maggs. I'm very happy to be the host here at Duke of this week's installment of the Triangle Distinguished Lecture Series. And we're very lucky to have with us Hari Balakrishnan from MIT. Hari's going to talk about vehicular cyber physical systems, or how to improve your commute. I've known Hari for a long time. He was a student as an undergrad at IIT Madras, and then he went to Berkeley, and from there to the faculty at MIT. And Hari is a Sloan Fellow, an ACM Fellow, a generally pretty good fellow. However, I think it's customary to malign the speaker a little bit before the talk, just to loosen up the audience. So I want to warn everybody about the dangers of writing a paper with Hari. So Hari he's very well known as being clever, and when you write a paper with Hari, you run the risk of being sort of left in his wake. So I twice now have been standing in a group of people when the discussion of a paper came up, and it was referred to as Hari's paper, even though I was standing in the group. And the discussion went on for some time before I realized that it was my paper. And then, got indignant enough to say, hey, wait a minute. But I didn't say it was my paper. I said, what about the student? Okay, the first author. However, I think it really tested my patience when I was asked to write a letter recently for someone who was coming up for tenure. And in his research statement, he cited this paper, except he left my name off the author list. Okay, so I'm going to turn the floor over to Hari. Thank you very much.
So thank you for inviting me to give this talk. And when I was invited, I was sort of thinking about what I really wanted to talk about. And one of the areas that I've been quite passionate about the past few years, since about 2004, is transportation. And I'm not a person who knew anything about transportation by education or training. And Sam Madden, my colleague, and I started this project and decided to work together on it, learning this as we went along. And the truth is that we've learned a lot from our students and postdocs who worked on this project. I also, when I first came up with the title, I sort of sent this thing off. I was going to send off the title just saying how to improve your commute. And then I ran it by a couple of people, and they told me it wasn't distinguished enough. So the real title of the talk is how to improve your commute, but the stuff on top, vehicular cyber physical systems, is actually the title of my NSF proposal that we recently got on this project, and thanks to NSF and other sponsors. But really, it sounds more distinguished. But it really fundamentally is about how to improve your commute. The next thing that bothered me was, I've never been to North Carolina before. I've read a lot about it, and it occurred to me that this may not be the talk that relates the most to the audience. Then I thought, people must drive here, and people must sit around in traffic, and maybe there's bad weather. Luckily, there is bad weather now, so some of what I'm going to say may resonate. But then I landed in the airport yesterday, and I saw this. This is an ad for North Carolina, probably from the tourism department, and it says, this is the closest thing you'll see to a traffic light in North Carolina. And then I thought, I think I picked the wrong topic. Sorry? They're lying. They're lying? Oh, good. So anyway, for those of you who think this is, the closest thing to a traffic light in North Carolina, let me just show you some pictures of what it's like in some other parts of the world. This is a picture from Boston, which is actually not even, I don't believe, anymore in the top 10 places where there's traffic congestion. I mean, it's pretty congested there, but there are cities in the US that are way more congested than this. I don't know how clear this is, but this is a picture of traffic in India. And actually, it is not clear how many of these are vehicles, how many of these are people, how many of these are, bicyclists. I mean, there's probably animals there, and it's kind of a complicated mess. But they are trying to clean things up a little bit in some of these countries, and this is not very visible, but what this is actually showing, if this were brighter, is that there's entire pieces of roadway here, presumably in the opposite direction, that are empty, and then here there isn't even place to stand. It's just completely packed, and it's just full of cars. The bottom line is road transportation is becoming a significant and big problem in many parts of the world, and this manifests itself as accidents and congestion and emissions and pollution and degrading civil infrastructure, and there just sort of isn't enough money to fix all of the problems. And the underlying driver for all of this is the enormous population growth. It's about 6.5 billion people today, and it's going to grow to more than 9 billion in 2050. What's interesting is that the growth in the less developed nations is quite a bit higher than in the more developed nations, and this gap is growing. But I really think that the place where road transportation is going to be stressed much more than it is here is in these other countries. 80% of the world's population is in places of the world where automobile growth is occurring at about 20 to 30% a year. I mean, in contrast, the automobile growth in the U.S. is not, it's not growing at anywhere near this rate, but there are parts of the world where it's growing at extremely high rates. Now, in the U.S. itself, there's been a lot more data that people have come up with and analyzed to understand what the traffic problem is. So, for one thing, if you look back about 20 years and you look at the morning commute and the evening commute, and you look at the portion of time that would constitute rush hour, in the early 80s, it was sort of an hour and a half of the day where that would be the case, whereas now in the top 85 metro areas, which is the place where this was analyzed, it's quite a bit longer in time. It's actually expanded by a factor of 2 on average, and in some places the rush hour is expanded by a factor of 3. And there's various definitions given to rush hour, and there's a whole metric around this called the travel time index, which measures the average time that it takes during peak hours and divides that by the average time during uncongested hours. And that metric is a number, and in some places it could be as high as a factor of 2. And that's just the average during rush hour to the average during off-peak hours. But the more interesting graph, this is from the U.S. Bureau of Transportation Statistics, where this is what this is showing is this travel time index, which is the peak to average time that it would take across the 85 cities in the U.S. As a function of time of the time of day. But what the red line is showing is what people do in terms of the buffer that they create in order to make a deadline. So let's say that I tell you that you have to get to the airport. Nominally you're 45 minutes away from the airport, and I tell you got to get to the airport at such and such a time. What people tend to do is to buffer that time in order to make a deadline, or you got an interview or a meeting and you have to make it by a deadline. And what this is showing is actually the amount of buffer that people tend to engineer for in terms of how they actually operate. So if you need to get to a certain destination, the amount of buffering that you have to add is much higher. And part of the reason for that is traffic is inherently uncertain. And it varies a lot. And therefore, in fact, anybody who comes up with a plan for traffic has to take into account this variability. But the other reason for it is simply that people just don't know. People have a perception that it takes a very long time, and sometimes it does, and sometimes it doesn't. And there are all these studies done of how they have people who travel on different routes. On one route, you just have somebody wait for 3 minutes at a light, and the rest of the trip is fast. And then you have another person who goes through sort of slowing, lots of stops, but no stop is of significant time. And the second trip is actually faster. And you ask somebody how long did the trips take, and most people will tell you that the trip where they had to wait for 3 minutes in one place was the worst trip. So people don't really have an inherent perception of any of this. Now, highway congestion costs a huge amount of money annually, and the transportation institutes have a particular way of calculating this, but it's a phenomenal amount. But here's some other statistics in the U.S. The average commuter travels about 100 minutes a day, which is actually an absurdly long time that people should travel. And in surveys done by various organizations, about a third of commuters say that they're stuck in very heavy traffic at least once a week. And this is often when they know that there's heavy traffic and they know to avoid it, and they still get stuck in heavy traffic. And in general, the worst case is usually worse than double the average in many of these cities. So the question is, what can we do about all this? So, transportation has been looked at for a very, very long time. And if you're sort of entering this field now, maybe you think that computer science and computing has something to offer the field. So what can you do? So here's some example applications, the ones that motivated us when we started and have motivated us as we've done our project. So the first is, systems that will help people reduce the amount of time they spend stuck in traffic monitoring and mitigation. Another one you can think about is how you go about figuring what road surface conditions look like. We call this subsystem the pothole patrol, which is, can you do something to discover where the potholes are and where the bad road conditions are? for two reasons. One is you can then tell users about them and route people around them. But more importantly, given that cities are perennially strapped of cash, everything is triaged. So you tell them, here are the most important bad road conditions that people can't avoid, and that's where you got to spend your money. It may not be wise to just spend the money on places where perhaps the zip codes where the highest taxes are being paid. I mean, maybe you should spend money on where people are not able to avoid problems, because that causes a lot more damage. So that's an example of something that one might come up with. Another is, in fact, to use the ability to tap into onboard telematics inside cars, which have hundreds of sensors and actually gather a lot of information. And one might actually be able to get this information and come up with a way by which you can communicate this information to other cars in the area to improve driving safety and do hazard monitoring. And that's another thing I'll spend a little bit of time telling you about. You might use the same access to vehicular telematics, the sensors in the car, to do preventive maintenance and diagnostics. I'm sure all of us who've owned a car at some point or another have seen the check engine light come on, and that just means you take it to the mechanic and spend some money, and more often than not, some sensor is flaky or something bad, not particularly bad, has happened. But every once in a while, something bad has happened. So how do you tell? Well, if you had the ability to actually have an online monitoring system that gathers all this information, you could tell. And in fact, you could make this much more collaborative, where you could just gather information from all the, let's say, Toyotas or Fords or Hondas or whatever of a particular make and vintage, and just compare the sensor values that are being reported. So the fact that a particular sensor is anomalous may actually tell you something relative to all of the other cars of the same make and vintage, in order for you to learn something about what's going on with the automobile. Fundamentally, I think that in many parts of the world, the way in which traffic problems could get mitigated is probably with smarter tolling, where you would do usage-based or congestion tolling. And one of the problems in doing that would be, there are two problems in doing that. One is that today, in order to do that, you got to put up toll booths everywhere, which is expensive because you have to put them out and man them and so forth. The other is that if you put them out everywhere, then people start being tracked. So an alternative to do this is to have embedded devices in cars, or even software running on people's phones that gets turned on as they drive, and at the end of the month, the state just computes your toll as a function of of the locations that you've been and the times that you've traveled, and they issue a bill. And the prices are all known. I mean, you can tell people what the prices are, or when they enter the roads, you can post the price up there. The technical problem is to solve this in a way that the state can compute the toll that you have to pay at the end of the month, but the state does that in a way that does not reveal all the places that you've been. And the other problem is that the state has to be able to do this without, even when you might maliciously tamper with the software. So, if you're somebody who's trying to save some money, you might decide that, I'll tamper with the software so that it'll report that I've not been at the places where it's expensive to drive. So that's something that we've developed a scheme for that will guarantee locational privacy, while at the same time being robust against malicious modifications to software that runs on the phone. And I do think that in the end, the ability to put embedded devices in cars or have software on the phone is actually a very scalable way to get smart tolling done. Another one that's quite hot these days is pay-as-you-drive insurance, for which, again, some of the privacy techniques that we've been working on are very applicable. Pay-as-you-drive insurance is when, if you're somebody under 25 in a college town, chances are you're paying way more than you should be paying for insurance. But yet, it's very likely that about 80% of the people in this demographic are pretty safe drivers. So I think there's a mutual benefit here. As one of those everybody thinks they're a safe driver. So if you're really one of those above average safe drivers, then you have an incentive in running this thing in your car. And the insurance company has an incentive because they just want, what does an insurance company want? They want money from people who never get into an accident. So the trade-off's a good one. So the deal is a good one, because you get a device you put in your car. The company monitors your driving behavior, and then gives you a break on your insurance. Now, when people tried to do this, companies tried to do this early in the U.S., they ran into this extreme storm of publicity, negative publicity around people's privacy, because now the insurance company knows everywhere that you've been. One of the techniques we've developed allows the insurance company to calculate this aggregate function that allows them to figure out how much premium you actually owe without you revealing your exact location tracks to them. And there's all sorts of applications that, in fact, computer scientists can, working across multiple areas of computing, can actually bring to bear on these problems if you have a sense of what the problems are, and if you're willing to, go and talk to people in transportation and other areas, like we've tried to do, to learn really more about what the real world looks like. So fundamentally, I think the reason why computer science has a lot to offer this area is threefold. The first is that mobile and embedded computing has actually come of age. It's now everywhere, and it's a lot faster than computers of just a few years ago. I think I was comparing the performance of my iPhone against the desktop computer that I had on my desk in 2002, and my iPhone's faster. So it's not, 2002 is not that long ago. And maybe I had an old computer in 2002, but it did the job it needed to do, and my iPhone is faster. So you all know this. This is just dramatic. Second one that's really important, I think that's even more of a significant improvement, is there's wireless everywhere now, and more or less we don't think much about it. It's just there. And the third, equally important thing is that there's ubiquitous sensing and actuation now, because you can actually tap into sensors very easily, and also tap into sensors that are on the automotive platforms, and there's lots of them, in addition to making your own, and in addition to using phones as sensors, because one way to think of a mobile phone is it's secondarily a communication device and primarily a sensor with computing on it. And there's lots of sensors that actually you can use. I mean, everything from a camera to an acceleration sensor to which you can use for vibration sensing and other such things. And ultimately, I think the way transportation will evolve is that it'll move away from this extremely rigid fixed infrastructure that they have today, where the model is that you might put sensors on the sides of the roads to understand something about traffic flow, and you put toll booths, and everything is fixed infrastructure. And you move away from that to something that's much more of a joint mobile and fixed infrastructure, because I do think that that's much more cost effective, allows you to deliver more personalized services, where if I know that you're doing certain things, you're getting up at 8:30, leaving home at 8:30 in the morning and taking particular routes, I can actually provide information about those routes to you, and ultimately much more efficient. So Cartel is basically a project that we started, Sam Madden and I started in 2004 to get at that, to build a system that would allow us to explore these ideas. And the idea is actually quite straightforward. There are smartphone software or embedded devices, small embedded device that we've built multiple versions of, that you put onto vehicles. And they just gather a wide range of information from their sensors and gather that at a very fine granularity. So this highly granular raw data collection enables us to, once you collect them all together, you can get aggregate details about the environment, such as traffic delays or bad road conditions or potholes or whatever. But yet, because there are individual tracks being provided, you can offer personal services. So I can, for example, discover when I travel and provide information about my routes and my commute times. So you deliver this to the internet. The transportation jargon for this is V2I, which stands for Vehicle to Infrastructure. And you send that over to servers that are, cloud is a new word. I just felt I had to use it here. But you send that over to servers on the internet. And a lot of the actions going on the servers, where they're trying to model what traffic conditions might look like and use that to predict what traffic conditions look like in the future and do various other kinds of analysis. And then ultimately you want to deliver these location-based applications to users, whether on a mobile phone or on a personal navigation device or on a website, but do so in a way that protects location privacy. And I mentioned some examples, and I'll talk through more of these in this talk. Some of the ones we've done are traffic-aware routing using stochastic routing, doing road surface monitoring by collaborative processing of information gathered from different cars. And this turns out to be both quite interesting and surprisingly hard in terms of all of the things that go wrong when you take your car and drive on the road, but only a small fraction of them are actually potholes or significant problems. But there's all sorts of things, including getting confused by people opening and closing the doors that might cause vibrations to occur. We've used this to think about ways in which you might rate driver safety. So give people a score from 1 to 100 on how well they're driving, which might be used for good insurance calculations, and a variety of vehicular telematics applications. And in fact, one of the deployments we have is with the fleet company, a taxi company in Boston, for which we provide some telematic services. And it's a good engagement because we provide them fleet management and telematics and give them information about all the things happening with their Priuses. They have a fleet of Priuses. And in return, we get a huge amount of data from that fleet network that allows us to do things like traffic monitoring and road surface monitoring and so forth. More recently, we're working on a project with Ford on vehicle-to-vehicle communication. Involving vehicular ad hoc mesh networks that one could use to improve the way in which network communication between these vehicles work. I won't talk much about that today. This is just more by way of context. So if you look at the processing pipeline, it's actually extremely simple. There's a slew of things that have to do with how you collect data, which involves sensing and communication. And it's like a crowdsourced model. The idea is that users, just regular users or taxis, carry devices or run software that gather information. And then all that stuff gets delivered up to something that does a lot of estimation and prediction, where the key technical challenge is handling a large amount of error that you see in the data, noise in the data, and high variance effects. So we spend a lot of time thinking about how to model traffic lights because they're not easily amenable to simple distributions, and how you deal with that. And one of the things I'll talk about here is how we can take noisy and erroneous information from position sensors and extract very accurate delay and speed models by matching those position values to a map. And in terms of applications, the fundamental challenge is coping with uncertainty in the raw data. And I'll talk about how stochastic routing can be made practical in the way we've implemented it in our system. So that's kind of the overall processing pipeline. And here's the outline for the rest of my talk. I'd like to spend time talking about 4 things. I probably may not have time for all of them, so we'll see how far I get. The first problem I want to talk about is how you can gather data at fairly large scale from a large number of phones and other small devices, where the data samples are inherently noisy and erroneous and maybe missing in parts, but use that to piece together a model of what speeds look like or delays look like on roads that's extremely accurate. I then want to talk a little bit about how you do that while guaranteeing user privacy, so that their location, I can gather this aggregate information and use that for a variety of purposes without knowing that you've traveled on this path and I've traveled on that other path. Then I want to talk a little bit about stochastic routing, and finally, if there's time, I'll talk about how road hazard detection works with collaboratively learning where the bad roads are. So in terms of the probe node, let me pass this around. One of the things we did was build a small probe node. This actually is probably the world's cheapest probe node. I'll explain what the pieces are. It actually has a commodity Wi-Fi access point that you open up and you take the board out, and we built a small board that sits on top that adds to it a GPS, a processor that will connect to the car's onboard diagnostic interface, so you can get all of the sensors in the car. It has acceleration sensor and a few other sensors. So you can actually even expand the board to add the sensors that you want. There are 2 things interesting about this. The first is that the only communication it has is Wi-Fi. And the second thing that's interesting about it is that because it's always connected to the car, it's going to drain the battery all the time because it's always connected to the car's onboard diagnostic interface. So what we built is uses a very low power small microcontroller with an attached acceleration sensor. So the idea is that that's extremely low power, much lower power than even all of the locking systems and everything in your car that remain on. And that's always on. The Linux processor and the Wi-Fi and everything is off. And whenever that acceleration sensor detects an acceleration event because you got into the car or somebody moved it, it turns on. And the PIC microcontroller then kicks the Linux processor on and it runs. And then after a while, if you've stopped and are quiet for 5 minutes or 10 minutes or something like that, it shuts the whole thing off. And what's interesting about this is it's extremely simple, but at the same time, I think it's a very good way in which you could keep something running all the time, but yet have a way by which you can detect when you want to do something. And one of the side byproducts of this was that you can actually use the system if you're stuck, if you're parked in a grocery store or someplace and you come back and you see a dent, you can at least know when it happened because you see that there's a vibration event and it actually shows up in the logs as something where, it vibrated at this point in time, it turned on, and you can go back and piece together where your car was at that time. So at least I don't know what good it does you, but at least you know that it happened here because sometimes you see a dent and you don't know when or where it happened. whereas this provides you the ability to get that completely as an accidental byproduct. What's interesting is the networking on it. We have a network stack called Quick Wi-Fi. I think it's actually the first sort of really practical Wi-Fi based network stack for vehicular connectivity, and this is really the way in which we primarily obtain information from the system. And the main contribution of this work is that it reduces the time it takes for a computer with a Wi-Fi card to connect to the internet. So today, if you're out on the road, it probably takes more than 10 seconds on any standard implementation, because it requires you to go through endless handshaking with the IEEE 802.11 protocols and ARP and DHCP and all of that stuff before you can get communicated. And we have a more streamlined pipeline that gets this down to under 400 milliseconds. And this stuff is deployed on a fleet in Boston, and I just wanted to show you a little bit of the view of what this fleet looks like. This is actually the current view of some of the cars on it and their locations. And what you'll see at the bottom is the set of cars. This time here shows the time since the last report from some of these cars as they're driving around. And this is relatively current, actually. And sometimes you can actually see, you can follow a car and you can actually see it. If it's moving, you can sometimes see it moving. This looks like it's parked. So actually, some of these cars have numbers on them. This 40% number here is actually the amount of gas that it has remaining. There's a lot of other telematic information that we can get from the car, including things like, how much is the driver pressing the brake too hard? Is he how well he's driving, and things like that. And this thing actually is the primary source for data in our system. And this car fleet that we have, mostly in Boston with a few cars in San Francisco, is really, in addition to some people using the iPhone software, that's the primary source of data in our system right now. The other thing is this iCartel. You're missing the I on the slide. iCartel is the smartphone application. And what it basically does is use a variety of position sensors, GPS, Wi-Fi, GSM, that's available on the phone, and the acceleration sensor, to essentially log information. On the face of it, this is a pretty straightforward problem. Let me actually show you what the iPhone application actually does. All right, so this actually, what it did was it started, this isn't a simulator but it's exactly the same application. It started this, and what you see here is the red, green, yellow from the data that we have, which is the sum number of iPhone users, and this the fleet that's carrying that device that's being passed around. This is the red, yellow, greens on the map that show you traffic conditions. The reds are basically when the speed is less than a third of the speed limit. The greens are when it's about the speed limit, and the yellows are between about 80% or so of the speed limit. One of the things that we do is traffic-aware rerouting. I'll talk more about this later, but what you can do is you can set up destinations on this map and ask for the system to provide routes. And the routes are computed using prediction that's based on current traffic conditions as they show up on the road, and a historical model of what the road traffic looks like. And if my network actually was working, what it would do is eventually come back with a traffic route. So I wonder if the network is... Try it again. All right. So what it did was... in the simulator, it assumes you're currently located in the center of Boston, and what it does is it goes and comes back with the route that you should take. For every one of these road segments, it tells you the time that it's predicted based on the route, and you can actually, as you drive, it sort of does the turn-by-turn thing. It takes you intersection by intersection together with the route, and as you drive, it zooms in and out of the thing. The other thing you can do on this is you can go in and click on different parts of the route, and it tells you the different pieces and the time that it expects to take. And one of the things we're doing now is focused on providing very accurate estimates of arrival time. So we're constantly updating the arrival time. The big difference between this and all of the other routing stuff, the Google Maps and so forth, is that this does rerouting dynamically. And it also builds into the way in which it picks these times. It uses the combination of historic and real-time model data for coming up with a model for what traffic conditions are going to look like at the time you travel. And it sort of does this forecasting using the methods that I'll spend a little bit of time telling you what these methods are. The other thing you can do is you can save these routes. And now we're working on something where you can save the set of common routes that you've taken, so that then before you get onto your drive in the morning, we can discover, we have a trip log that you have access to, where we keep track of the common routes that you've taken and the times at which you travel. So before you get into the car, you might get notified by an SMS or an email about something that's going on. And the other thing that the application does is integrate with your calendar. So if you have a meeting somewhere at a different location and you put that location, what it does is it looks at that and figures out how much time you need to travel and adds a buffer onto your calendar. And there's a link on your calendar. If you click on, you get the turn-by-turn navigation for that. So it integrates with the calendar that runs on your Apple device as well. So by putting all of this stuff together, I think it makes sense, because it's unlikely that people are going to be using just a pure navigation system when it's their regular commutes, where they sort of feel like they know the route. So something that tells them something out of the ordinary is something that's probably got much more useful than, I don't think people are going to be using the navigation system on a daily basis just to go on the regular routes. And I think by integrating with the calendar, it makes a lot of sense to me, because that allows you to plan when you're outside of the car. And then once you get into the car, you can use that to a new place if you need to get driving to a new place. So I do think that this kind of idea where the sort of traffic-based applications integrate with the rest of the stuff that people use is the right way to deliver these things to actual users. So this thing actually is on the App Store, though it really only works in Boston, because that's what we're focused on doing. So we're probably going to rebrand it and put it out back onto the App Store as Boston Traffic, and then go city by city. Because, when we put it out on the App Store, we got a lot of downloads, but then there were people saying it only, it doesn't work here and doesn't work there and doesn't work in some other place. And I think that's true. So we want to start with a couple of cities and do a good job of that, and see how it works with regard to whether the rerouting capabilities that it has and the predictions that it does are better than the other stuff that's out there. So I'm just going to skip these screenshots. So what is the actual technical problem here? Because on the face of it, you're gathering the GPS information, which is not such a big deal, and delivering it up to the server. So there's really two problems. The first one is doing it in a way that doesn't drain your battery. And the second one is figuring out how to combine historic and real-time data to come up with the actual right traffic model. I'll talk a little bit about the second problem here, but I'll spend more of my time on the first one. So here's a crude way you could look at energy versus the accuracy of position samples. And this is true for the iPhone. It's probably true for some other phones. And I make no representation that it's true in general. I think Romit has done some work on this, and I think some of these experimental findings are consistent with what we found. So if you look at energy consumption, GPS has pretty high energy consumption on many of these commodity devices, but a pretty good accuracy. At the other end, you could use your GSM, your regular cell phone radios. So the incremental cost of energy is extremely low, but the accuracy is not all that great. And Wi-Fi is sitting in the middle, because you could use, it's pretty easy to get Wi-Fi location databases and use that to figure out your location. And the accuracy is probably on the order of 50 to 100 meters. So really, one of the things you could imagine doing is that when you're going on a straight road and you're going on that road and the system knows you're going on that road, you can just turn off the GPS and use the low energy sensor to sample things. And then every once in a while, when you get confused, you could turn the GPS on, get a fix, and you hope it's correct. Though, frankly, in downtown Boston or New York or Chicago or any of these cities with tall buildings, it's unlikely that it's always going to be correct. So But what you can do is to use that combination to come up with an algorithm that would do the right thing. And there's lots of algorithms one could come up with. We have one. But the important thing is that you're going to get data that has noise, that has outliers on it, which are quite common, and outages. You enter a tunnel and the thing doesn't work. And at least in Boston, the tunnels actually have a network. So now you kind of have to figure out where the car went, which is an interesting problem. So what VTrack does is solve this problem, and it does it using a two-step approach. And here's a schematic of what VTrack does from some real data. So there's a car that started off at this end and went through like that, and these were the position samples that we found. And this is a combination of using Wi-Fi localization. And in fact, in some areas around here, the GPS just puts you in the middle of the river. So you sometimes don't quite know where you are. And what you want is an output that looks something like this. What you want is the algorithm to pin you to the most likely path that you did take. And so that process of figuring out the segments on the map that you likely traveled on is map matching. And once you determine the most likely trajectory, you actually want to estimate the delay or the speed on those roads. So you want to assign fundamentally each observation to a road segment where the observation was most likely gathered from, and then extract the delays from it. So our method for doing this, our software for doing this, is called VTrack. And actually the way it works is an application of a hidden Markov model. So, by the way, before I do that, the other thing you have to do is when you have outages that might happen because of urban canyons or GPS went off, or the other thing is, at least on the iPhone, you're driving, somebody makes a phone call, you pick up the phone call, the software stops working because right now we don't get the ability to run a background application. So there's all sorts of real-world reasons why this happens. On the Nokia phone, if the thing is deep inside your pocket, the GPS manifests itself with outages. It works, but sometimes it just has gaps in the middle. And you'd like something that just provides information no matter what happens, and give you, you can interpolate and then produce the map again. So in any case, it's an application of a hidden Markov model, which is a very old idea that's been used in a number of contexts. So schematically, if you have road segments that look like this, and you see points P1, P2, P3, and P4, and these points tell you that they're at these locations. Now, these points may come about because you have some Wi-Fi location database or a GSM database that believes that if you see this pattern of access points, you're at that location. And oftentimes, these will put you off the road because they're gathered by people who are walking around, who may be inside shops, who may be on the side of the road, and they just take some sort of a centroid of different locations from where they saw a cell tower or an access point, and they tell you that they're over here. And in our own system, we've gathered about 600,000 and probably more access points, non-GPS location access points from in Boston, and you end up with data that puts you at weird locations, close to the road but not necessarily on the road. So let's say you saw P1 and then you saw P2 and then P3 and P4. What's the most likely thing that happened? Well, probably the car went this way. It's possible the car went the other way. We're just interested in the most likely outcome, and then we're interested in knowing what the probability of that is. So you can assign, come up with one of these big hidden Markov models with transition probabilities, and it turns out it doesn't really matter what the transition probabilities are as long as they're reasonable. So you don't have to spend a lot of time figuring out, am I likely, what is the probability with which I undergo these transitions? And one of the consequences of these models is, in fact, that at least for this application, they're totally robust against, you can start with almost anything. And then you apply a Viterbi decoder to it in order to get the answers out. And the weights on the Viterbi decoder model the noise process. And so it turns out that for GPS errors, when there are no outages, just errors in GPS, empirically Gaussian distributions work pretty well. It isn't a good model for Wi-Fi, so you massage the Wi-Fi errors a little bit to come up with a slightly different model for what the errors are. And then you do the same thing. You just apply these error terms, or the square of the error terms, as the weights on the hidden Markov model, and apply a Viterbi decoder to produce this out. The interesting thing about what we do is that we want to make this work in real time, because one of the goals we have is that as you get data from large numbers of cars, what you'd like to do is to produce a delay model every 5 minutes. So what we're doing is applying this in real time, and there are some interesting effects that sometimes happen where the car is traveling around, you think he's going on a certain route, and you provide a delay model, and 5 minutes or 10 minutes later you discover, guess what, the car actually went on a somewhat different route. So you go back and update the old model, because the thing about these kinds of Viterbi decoding is that future information tells you a lot that changes the old stuff. So how you deal with that and how you set up the databases to do that is an interesting problem in order to do this in real time. And the approach of simply putting everything in a relational database and going back and forth from it turns out to be slow, so you want to end up with doing a bunch of stuff in memory and then putting things back in the database. In terms of noise, this one is not that interesting. You model the probability of transitions and you also model this error metric. The outliers are dealt with by speed constraints. So many of the outliers are simply, you can't be driving at 85 miles an hour on a city street. I suppose you could, but it's not realistic. So you just find the normal outliers. And for outages, you do various interpolations. So one interpolation you can do when you have an outage is to determine the most likely path that the historical data showed people took between this location and that other location. The other thing you could do is to find the shortest path. The third thing you can do is to simply draw a straight line. It isn't on a map. You just draw a straight line between them. And what has been extremely surprising to me, though not to the student who came up with that idea, is that putting the straight line between 2 points oftentimes wins over, not wins, but certainly does at least as well as things that are far more sophisticated that involve actual routing. Now, why that is, I think, has to do with the way in which road topologies are constructed. And in fact, many times there are a relatively small number of ways you can go between places. Though in theory you could do, the map looks quite dense. In practice, there are only a small number of things that people actually adopt. So a little bit of history together with just connecting the two with a straight line turns out to make the computation extremely fast. So VTrack works actually really well. We've collected a huge amount of data, and a subset of it is about 800 hours is analyzed here. The main result is that we can use this to predict delays, and it's about a factor of 3 better than a variety of previous approaches. And it gets better and better at the tails of the delay. So delays that are long, it does a much better job of predicting. And the delays that are longer than normal are the ones you really want to spend all your, that's the stuff that really matters in practice. The other thing is that we define hotspots to be places where there is road traffic congestion, significant traffic congestion, where the variance is extremely high. And this method is able to detect hotspots, 80% of the hotspots correctly with about 5% of a false positive rate. And as in all these systems, you can trade these two things off against each other. So overall, I think that the method actually is quite good and robust, and that's the thing that's actually at the back end of the iPhone application and the rest of our system. So the question right now you could ask is, so what of privacy? Because now the model is that all these phones are carrying something that deliver information up to the server, and the information they're delivering is location and time and location, and time, location, and speed. So now this totally violates location privacy. So the question you can ask is, can the server derive aggregates without violating privacy? And also you can ask, what functions can the server actually calculate? Like the tolling example. So what you want is efficient ways to compute functions at the server, but you want the system to be able to compute it while being robust to side information. So what I mean by side information is stuff where if the server knows, for example, that Bruce lives on such and such a street, just because he knows that information somehow out of band, and that Bruce is the only user of the system on that street, then whenever any information comes from that street, the server knows that Bruce has arrived or left that location. So that kind of side information is what you want to guard against. And we spent a lot of time trying to define what that means, and also what it means to provide privacy in the presence of side information. Because remember, we don't know what information the server actually has access to, but we can model it as, does he have information about whether users are at a particular location? And that's a good way to abstract this. We also want to be able to make sure that the server doesn't get fooled by malicious or buggy mobile nodes. So for example, in the traffic congestion problem, you might have an incentive to report that there's very high congestion near your house, because that makes sure that nobody will use those roads, or other such things. And so you want something that's robust against that. So PrivStats is the scheme that we have to compute aggregate statistics such as speeds in a way that preserves location privacy. vPriv is a scheme that can compute any additive or multiplicative, well, it's not additive or, it's additive functions with maybe 1 or 2 multiplications that are a function of a location stream. So I give you a set of GPS points, and I want you to compute a function of those points, and I can find the correct answer without knowing the actual locations that the car has been on. So let me tell you a little bit about how the aggregate stuff works and just give you a flavor for the idea. So the first thing is, of course, that you mustn't include the identifier of the telephone or the user's device in these reports, and that's pretty obvious. But of course, the aggregator can still learn side information about this, about what's going on, like I described before. So if only Alice lives on a certain street, and you see an incoming tuple, you know something about Alice. So you can now do one of two things. You could design a system to provide plausible deniability, which is that there's some data, but you can plausibly deny with extremely high probability that somebody else could have generated the data and not you. Or you could actually think of wanting to provide complete guaranteed location privacy, where the server computes certain aggregate statistics but doesn't know much about, doesn't know anything about the location. So the short summary of the result is, actually I think it's on the next slide. Let me first tell you what the plausible deniability idea is. And I actually think that the plausible deniability plan is probably quite practical and probably what people might be happy with in practice. So suppose by some side information the server knows that there are only 2 users of a road. Now, if both people send data, then clearly there's no deniability anymore, because there are only 2 users, there are 2 different reports of data that came in, so you don't have any deniability. And in general, now, if by side information you know exactly who the end users of a road are or end users of some part of the system are, if they all report information, you're actually in trouble. So it isn't the case that if there are a large number of users, you can sort of hide and just report information, which is sort of an intuition that some previous work has adopted, where they've said, oh, look, if I know that this is a busy road, just report information. Because in fact, that may be the wrong thing to be doing, because if everybody who uses that road reports information, then you actually have no deniability. So in fact, to provide plausible deniability, you must ensure that not all of them send data. And what's interesting is it turns out you can quite easily do this with high probability. You could arrange for something where with high probability you could make it so at least one person does not deliver data, and work out what the probability with which you should send data is, such that by composing all of that stuff together you get the probability that one person doesn't deliver the data. And now, you can provide the guarantee that at least one person does not deliver the data with as high a probability as you want. Now the other thing you need to do is, remember I talked about this VTrack algorithm and all the stuff where the data gets noisy and all that stuff? Well, that has to run, as I described it, it runs on the server on these streams. So for you to really have a plan for privacy, you actually need to push that computation down onto the phone, because the phone is the one that's now going to be getting your tracks. And every once in a while it determines that it's on a road, it flips a coin, determines a probability based on some knowledge of how busy it thinks the road is to work out a probability, and then sends information up to the server about the speeds on road segments, stripping out all identifying information. But much of that computation runs, the tracking computation runs actually on the phone. And one of the things we're looking at now is how you split this computation between the server and the client, and asking, what's the most you can do on the server while preserving privacy, or do you actually have to run all of it on the phone, on the device? Now the question is, can you do better? And the answer is, you need a little bit of help. So you can apply homomorphic encryption, which allows you to compute functions. You can add 2 numbers which are encrypted and provide and come up with an answer that's encrypted, and then decrypt that answer. And we've actually built that to run here. But the trouble is that the people who drive on a road, who report information, need to actually trust somebody to decrypt it. Now that isn't the server that's doing the whole thing. It could be your own home PC that does the decryption and then pushes up some information to the server. So it's some auxiliary third party that's purely trusted with decrypting your answers. And then that decrypts the answer and sends the thing over to the server. And to us it appears that absent a semi-trusted auxiliary, it appears that it is impossible to provide full location privacy. You can provide plausible deniability, which may be good enough without any third party, or you could provide something much stronger in terms of a privacy property from a cryptographic standpoint, but you need a semi-trusted auxiliary service to do a little bit of extra work. And I don't know, we don't have a proof of this, but it's a pretty strong conjecture that I think, well, we'll find out if it's really true or not. So let me spend the next few minutes actually telling you about traffic-aware stochastic routing and show you a little bit about what we've done. So traffic aware routing. So what's the reason for traffic aware routing? If you look at mapping systems, this is from our own system with red, yellow, greens, or Google Maps, or any of these systems. They all tell you red, yellow, green, but it's totally not useful for anyone because it's not clear. First of all, a lot of it is current information, not something about the future. But even when it is, I mean, it's very hard. I mean, maybe a few people can compute good paths based on that knowledge, but most people are sort of looking at, oh, I see a blotch of red here, I should avoid it. But that's really not a good way to do it because oftentimes that blotch of red may be just one place where it's congested, but you're actually okay going by that path. The other thing you could do is to buy one of these GPS devices. I spend some money buying a real-time GPS traffic service, and usually it tells me that I'm in a traffic jam when I'm in a traffic jam. I mean, you're there and it's getting this information, and it doesn't really embed very much in terms of rerouting around something that's a little bit further out in advance. So I think you want something more than I'm right now in traffic and a bunch of color-coded maps. So this is clipped on the left, but let me tell you the three challenges as I see them, some of which we're addressing, but many of which still remain open. The first is that traffic delays are fundamentally uncertain and variable. So I think modeling costs as fixed numbers is not as good as modeling them in terms of distributions. The second is that any routing system like the one I showed you with my iPhone application should do dynamic rerouting. So our system actually reroutes you based on whenever it believes that the estimated arrival time is different from what it told you, or when it thinks that congestion has occurred or changed. And the third is that at scale, these things become quite interesting. This is the classic question. Okay, great. If the 10% of the people are using it, maybe they benefit. What happens if everybody uses it? And I think the question of multi-user routing in a stochastic context, as opposed to over fixed cost networks, is still quite an open question and something we've just started addressing. So stochastic routing is actually an old classic area of work. Where given a travel deadline, one representation of the problem is you're given a travel deadline. I got to get to the airport by 5 p.m. Maximize the probability of reaching the destination within that deadline. You have a dual version of that as well. And the bottom line is you can use this to provide credible routes. And it's a hard problem because the standard routing techniques around A-star or Dijkstra's, which is what every mapping system and routing system uses today, don't apply for reasons I'll explain in a minute. This is an old problem. I think the most recent, I think for a while people have generally believed this to be largely either of academic interest or somewhat intractable. But I think a few years ago, Eddie Nikolova, who was an MIT PhD student, who actually is a postdoc with me now, came out with, I think, what were very interesting results that certainly caught my notice, and we've managed to use that to build practical systems. Not exactly her algorithm, but certainly her insights. We've adapted that and changed that in ways I'll describe. But I think what she finally showed was something that, a set of results that I think make it very attractive for practical systems. So here's the network model. You have a graph with probability distributions on edges, and these are delay distributions. So this is the probability that the delay on this edge is a certain value. So it's just a standard density function. And let's just assume, purely for theoretical ease, that the delays are independent and Gaussian, and that's just to prove certain things about it. The algorithms actually work even otherwise. And you can do certain things to real road networks and we've done by grouping segments together that actually make the delays look independent. With regard to whether they're Gaussian or not, I mean, they're not actually Gaussian, but it turns out empirically it doesn't matter all that much, in that they still work really well. So what you'd like to do is to find paths that, given a deadline, maximize the probability of reaching within that deadline. Sure, what's that? So one way to think about this is that what you're really, assuming it's Gaussian, this is the tail probability, 1 minus this is the CDF of a Gaussian distribution. So what it really says is that find me something that minimizes the probability distribution that's greater than the deadline that's at the tail, which is the same as maximizing the CDF, that's the cumulative density that's in front of it, which turns out, if you know the duration, the deadline d and the mean of your path, pi here is a path, so this is the mean travel time on a path, it's d, the deadline minus the mean travel time over the square root of the variance. So you're trying to find paths that maximize, you're trying to find the path that maximizes this number across all the possible paths. And this is really the problem that has been around for quite a while, which Eddie Nikolova looked at. And the difficulties here are that the optimal path depends on the deadline, and the optimal substructure that you do for normal routing doesn't hold. So the best answer from A to C, if it goes through B, well, the subpath from A to B may not be the right answer. So you can't do the standard things that you do. And it also depends on the actual deadline that you apply. So the interesting thing about her work that we apply is that if you draw a graph of the variance of the path, so you take every path in the network and you plot the variance of that path against the mean of that path, you end up with lots of points like this. And the interesting thing here is now if you start looking at maximizing that, you end up with something that's quadratic. The variance is a quadratic function of the mean. And what that means is that you pick a deadline and you find all the possible parabolas that start at the bottom, whose minimum is over there, and you keep opening that up. And the first point that it hits here is the right answer. So as you sort of change the curvature of these things, you hit one of the paths, and finding this path is the thing that you want to find. So what she showed, what Evdokia showed in a very nice result is that there are n to the log n such points. And then she had a way of coming out with finding these. The trouble is n to the log n is kind of good in theory, but it actually is too big for even Boston and Cambridge together, where you might have tens of thousands of nodes in a network. But it's actually a pretty good start because it actually allows us to do things that were previously, I think, much worse. So what we did was to take that result, and we came up with a way to apply parametric optimization to it, but more importantly came up with a way to prune paths so that you would go and navigate the search space in a way where you would apply different lines here of different slopes and come up with a way to search the space that actually turns out to have much smaller running time and is much more efficient. And that's the method that we actually adapted and use in our system. So as an example, I mean, this is in the Boston area, going from one end of Cambridge to another. We can actually set a probability, and we tell you, here's the probability of arriving within 20 minutes. And we've done some experiments using all our data to demonstrate that, in fact, these results will hold. In contrast, existing navigation systems don't provide any such guarantee. And they may take you on paths that have very high standard deviation, even when their expected value is low, which means that you actually end up with a far greater time more often than not. I'm going to skip that. The bottom line is the path also depends on time of day, so our system is actually adapting to various times to time of day as well. So I'm actually going to skip the part of the talk that talks about road pothole detection, though it's fun, and wrap up here. Overall, what we focused on is to understand how computing can help transportation systems, and I think we can do that in three ways. Data collection using sensing and communication, a variety of algorithms for estimation and prediction, and a variety of applications that cope with uncertainty. But overall, I think the bigger, broader lessons I've learned are the following. First of all, this is still ongoing work. But I think, first of all, the current approach to transportation I don't think can scale for much longer for many of the reasons I explained before, having to do with how traffic is growing and how automobiles are growing on the roads. And I do think we have a lot to contribute, but many areas of computer science are represented here in addition to network systems, which is my own original area of work. I think there's a lot to be said for how algorithm design, such as the one on stochastic routing, can be used and made practical, machine learning, cryptography and privacy, and embedded systems, all of which I think contribute a lot. And I do think that this body of work around vehicular cyber-physical systems, I think, are only just beginning to have an impact, and I think we'll see a lot more of this in the coming years. So thank you.